All right, let's have a little look here. So, the test, go ahead and click them all the way closed, have a look please. So the test is in two parts. The, see all of them close please. Thank you. So, in two parts, I'm going to just briefly go through the first stuff that we covered. Early in Unit 3, we talked a lot about functions, right? So we did things like determining if that table represents a function or not, determining if a graph represents a function, writing from a graph, writing the domain or the range of a function, finding intervals where it's increasing and decreasing, etc. Stuff like that, right? Pretty straightforward stuff. I don't want to spend a lot of time on it. We've already spent a lot of time on this stuff, but I want to just very briefly review it with you. So real quick, is this a function? Why or why not? Okay. I'm hearing no, which is correct. How come?
Because all these ones that are multiple.
Okay. So a single input, 3, maps to multiple outputs. So that's not a function. Remember what the single criterion for a function is. For a function is, it's not a function, or it is a function if for every input there's only one output, right? In this case, for the input 3, there are multiple outputs, so it's not a function. How could we tell with a graph? Vertical line test. Yeah, we just sweep a vertical line across the function. And it could be a continuous function that looks like a normal graph, or it could be a discrete graph where we just have points. Doesn't matter. The same test applies. If I sweep a vertical line across this, if it never intersects the function in more than one place, or the graph in more than one place, it is a function. What about this one? Nope, we got a problem, don't we? We got a problem right there. See, those points line up vertically. So that violates the vertical line test. So, maybe I'll make a note of that. So fails. Okay, how about this one? So now they want the domain of the function. What's the domain? Set of all what? X values, right? So domain goes with X, what goes with Y? Range, okay? So the domain is going to be all the X values represented on this function. This function goes forever, right? There are no endpoints graphed on this thing. So if I were to take this infinite function and squeeze it all into the X-axis, how much of the X-axis would it cover? All of it, right? It goes to the left forever and to the right forever. Yeah, it's going up and down and doing some vertical stuff too, but all we care about is how far to the left could an ant walk? Infinitely far, right? How far to the right could he walk? Infinitely far. So if I were to squeeze it onto the X-axis, it would cover everything. How do we say that? How do we say all real numbers as an inequality? X is greater than what? If it includes every negative. Good. And less than what if it includes every positive? Okay, I heard it, infinity. Or if I want to write that using interval notation, remember I could just write it like that also. This is the answer that they're wanting here, isn't it? Inequality. Okay? How about one like that, where it doesn't go forever? What are the only X values that are represented here? If I were to squeeze this onto the X-axis, what would it look like? Where would the interval appear on the X-axis? From where to where? -2, good. Up to 0. Now, what kind of endpoint would I put here? Open, because the endpoint is not included, right? So the X value -2 is not part of the graph, and ant can't stand there. There's a hole in the function. How about the other side? Closed, because that is included, okay? We want to write this as an inequality. What does that look like? X is greater than what? -2 and
Less than
or equal to 0. Good, if we write it using, that's what we wanted, an inequality. If we were to write it as an interval, we'd get open, rounded parentheses, open parentheses, and a closed bracket, right? Make sense? Okay. How about the range? So range, you told me a second ago, was a y value instead of all the y values, right? So if I were to squeeze this onto the y-axis this time, because we're talking about y values, what would the graph look like? It would start where and end where? -10, all the way up to what? -4, okay? And we know that because that's where those points would get squeezed, right? What kind of an endpoint do we have at -10? Open. Because neither one of those are closed. If one of them were closed, then it would be closed, wouldn't it? Because an ant could stand at y equals -10, but he can't here. What about the top? Good. So how do I say that using an inequality? Y is what? Greater than -10 and less than or equal to. Good. Using interval notation, what kind of, in this end I've got rounded or square? Very good. Round on this side. Good. So then it's just, I gotta put the lesser number first, like a number line, and the larger number second, right? Just like that. Okay? So we're looking at increasing, decreasing. So what about this one? This is kind of a little bit tricky. Now, this red thing is an asymptote, right? So it's telling us that as the ant walks to the left forever, he never quite gets up to a value of y equals -4. He's always a little bit below that, a little bit less than that, but he gets closer and closer with every step. So then if I had an infinitely smooth surface here, right, and an infinitely smooth marble, and I set it on top of this thing, what would it do? It's going to roll which direction? It's going to always roll to the left, isn't it? Right? Maybe very slowly, but it's always going to roll to the left because it's always going downhill a little bit, isn't it? Right? So where is it increasing? What do you think? Where's it increasing? But increasing, remember, that means as we walk in the positive x direction, we're walking uphill. Are we ever walking uphill? No, we're always walking downhill, aren't we? It's decreasing everywhere. So it's increasing nowhere. Right? B and A. Okay, how about something like that instead? Where is this one increasing? So it just means where is the slope positive? Where are we walking uphill from left to right? What do you think? Where's an ant walking up? Is an ant walking uphill at -2? No. How about -5? How about -1 trillion? Yeah. Okay, so this whole part of the function over here, this whole part is, he's walking uphill, isn't he? He's coming from negative infinity and walking uphill. When does he stop? Right there, right? When he gets to the top. So at that point, x equals -3, that's the transition. That's where he reaches the peak and he transitions from uphill to downhill, right? From increasing to decreasing. Where else is it increasing? Okay, starting at 2, well, that's the transition point. It's flat there. It's actually not increasing, but every point to the right of that is increasing forever, right? It just goes up forever then. So how do I say those intervals? X is what? If I squeeze those onto the x-axis, wouldn't they look like that? Right? How do I say those? As inequalities. So x is what? How do I say this part? X is, how do I say, what's my math word? Less than -3? Okay, -3, or, remember that's just or. How about this one? X is greater than 2. Good, so there's my answer. Okay, good. Where is this function negative valued? Where is the function negative valued on the xy plane? No, not decreasing. This isn't an increasing, decreasing thing. Just negative value. The function is, f of x equals y, right? So in other words, we're asking, when we ask where a function is negative value, we want to know where are the y's negative. Well, where is that? Where on the xy plane is y negative? Always. What do you think? Jade, where's y negative on this xy plane? Are y values negative there? No? How about there? How about there? How about there? Okay, you're right. So what do these two places have in common down here? Below the x-axis, right? The x-axis, when x is 0, that's what, or when y equals 0, that corresponds to the x-axis, doesn't it? Every point on the x-axis has a y value of 0. Every point below has a negative y value. So we're looking for the parts below the x-axis. That would be the parts there and there, right? Now, what about at x equals 4? Is it negative there? No, if it's 0 there, so I won't include that point. And at x equals 7, it's 0, so I don't include that point. But what x values are we talking about then? What are the x values where this function is negative value, when x is what? How about this part over here? What do you think? Caitlin, how would I describe, what are the x values for that part of the graph? X is less than 4. Yeah, good, right? When x is less than 4, the ant is to the left of 4 and is below the x-axis, right? So x is less than 4. Now we got another one, so we need to put an or in there. How about the other side? What do you think? Good, what do you think? How do I say this part? X is less than 7? If x is less than 7, that'd be like x equals 6. X equals 6, he's above the x-axis there. But greater than 7, like if I pick 8 or 9 or 10 or a billion, he's going to be way down there somewhere, right? So x is greater than 7. And think about it in terms of what if I squeeze, this part of the function onto the x-axis, wouldn't it just look like that? Or if I squeeze all these points, if I squeeze them all up onto the x-axis, it's just going to look like that. Right? Those are the intervals where the function is below. Right? Okay? End behavior. So really simple, but it's just something we got to be familiar with. A very, very simple concept. As x approaches negative infinity, that means we're going forever in which direction on the xy plane? To the left, right? So as we go to the left forever, we want to know f of x. Well, that's just y, right? Y is doing what? If I go to the left forever, what's the graph definitely doing? It's going down, right? Going down forever. So my answer is negative infinity. Yeah. Okay. No big deal. How about this one? As x approaches positive infinity, so as I go to the right forever, what does y do? It's pretty boring. What does y end up approaching? Yeah, it looks like it's just more and more closely approaching that asymptote. And what's the y value there? Well, 0, right? That y value, there's y equals 1, there's y equals negative 1, that's y equals 0. So we end up with, as x approaches infinity, f of x approaches 0, right? Y approaches 0. And the y value just gets very, very consistent. Okay, how about this? Very simple again, just some terminology I want you to be familiar with. So if you pull this menu down, the options are minimum or maximum, or neither. So what does this have? A minimum or a maximum, or does it not have any of those? It's got a minimum. Okay, it's got a minimum where? Yeah, -6, +4, right? Just at that location. So we have to write it as an ordered pair, right? So it's a point. Okay. All right, so now we're on to this stuff. So here's the part that probably where you need the most review. So how are we gonna choose a graph? I just chose some of the harder ones. There's some easier ones too. But we gotta think in terms of what we're gonna do with this, right? We wanna start with a parent graph, and then we're going to tweak it to do this. What's our parent graph here? X squared, right? So we're starting with, the basic function that we're starting with is p of x equals x squared. Now, what are the things that we're doing to it? There are three numbers up there that we've introduced into this parent function, right? What are they? I mean, what do they mean and what are they? What is the 6? That's a, isn't it? Good, so we know that, one thing we know is that a equals 6. What about these other two? What do they tell us? Okay, good, so what are the values of h and k? What's h? 2? Because that's the value that's subtracted from x, right? Okay. And what's k? 4. That's what's being added at the end, right? If we were to kind of just write this function in terms of a's and h's and k, it's just matching that pattern, isn't it? X, a times x minus h squared plus k. So now we just have to figure out, okay, how do these three values, a and h and k, how do they take our basic parent graph and make it different and transform it, right? So let's look at that. All right, so okay, what did we say the function was? 6? What were they again? Okay, 6, 2, and 4. All right, so let me write this in there. Six times x minus 2, is that what it was? Squared. Plus 4. Okay. So first thing we have to do is we have to remember what our parent graph looks like. Right? We have to remember what f of x equals x squared looks like. And that's super easy, but you just got to know it. If you don't know it, you got to get it. And it's like I say, it's not hard to do. But it's in the notes. I've got it. It's in the notes I've published from my lecture notes, like about 1 billion times. It's in the reading that goes with the book. So if you're not familiar with it, get familiar with it. If we take a basic x squared graph, what are the important points? Where's the vertex on an x squared graph? Origin. So 0, 0, right? What's the next convenient point? 1, 1. Right, and that makes sense, because if I plug 1 in for x, 1 squared is 1 for y. What's the next one? Come on now, this is like algebra 1 or pre-algebra stuff. You know this. What's 2, 4? I put in 2, I get 2 squared is 4, right? Then I'd put in 3 and get back 9. So we know these points. They're no big deal. There they are, right? There's at least 4 of them, right? If we connect them together, we know that that's what the parent graph looks like. That's x squared. Now, what's the order in which I've got to do this stuff? What do I have to do first? Do I have to, what does A do, by the way? Say it again. Dilation factor, vertical dilation factor, right? So it's going to stretch or compress vertically. H and K, what are those? So you could think of it as the vertex, but to get the vertex from the origin, we had to translate it horizontal and vertical, right? So horizontal and vertical translation. You guys should see phones away, please. Okay, so what do I have to do first? Do I dilate or do I translate first? Because this is really important. Technically, I have to dilate first. Technically, I have to dilate first, and then after I stretch it, then I can slide it where it goes, right? Now, we can cheat a little bit, and we could actually decide, okay, we're going to translate it first, but then from that point, we're just going to pretend that the vertex is at the origin, right? But technically, we really should. I mean, the math gods would tell us we've got to stretch it first in this case, and then slide it to where it goes, right? So let's deal with the dilation first of all, the 6. So how's that going to go? If I want to stretch this thing by a factor of 6, what does the vertical dilation factor do? What's its job? How does it stretch something? Okay, so I'm going to pull these points up, but how do I know how far up they go? if A is equal to 6, what does that mean? Say it again. They go up and down, so does that mean I can slide each of these up 6? That's not quite like that though, right? Because the dilation factor, a factor is something that's multiplied. That's the meaning of a factor in math. Okay, you want to help us though? What do we do with this 6? Stretch it, but how? How do I know, for example, let's take this point right here. So we've got this point at 1, 1. How do I know how far to stretch it? 6 times 1. I'm multiplying the y values times 6, right? So whatever the parent y value is, so 1 is the parent y value, right? I'm going to multiply that by a, which is 6. And I get back 6. Actually, let me make that in blues, I think the next. So I'm going to multiply that times 6, and I'm going to get back 6. So this one's going to be 1 times 6. It's going to go clear up to there. How about this one that starts at 4? 4 times 6 is 24. So that one's going to be off the chart, isn't it? So that's going to be way up there at 24, right? Okay, and we can see that. And then the one at 0, 0 times anything is, so that one, of course, stays put. You see the problem, if I translated it first, even the vertex would get stretched, right? Okay, so we want to dilate first. So don't we end up just getting something like that then, right? Oh, the wrong one up there. No wonder. Hold on. Okay, that's the one I wanted. All right, and then there's the dilated one, right? So instead of this point being at 1, 1, it got moved up to 1, 6, just like we said. Okay, it got stretched up there. The whole thing got stretched up. So there's the A part, right? The H and the K part are easy, right? The H and the K, those are just telling us where we're translating this thing. 2 to the right and 4 up, right? So that's easy then. All I got to do now, if I want to translate this thing 2 to the right, I'm just going to let H equal 2 and K equal 4. And then all I have to do is graph it, and look what it did. It just slid that point up to there, right? Okay. The other points do exactly what you'd expect, right? I know that if I start at the origin, you guys already told me that normally I would go to the right by 1, and I'd go up by 1 and be there, but we had to multiply that 1 times 6, so instead I'm going up 6, right? So the shape is the same, right? So what we really could do is we could say, okay, let's go ahead, if we want to do this one time on graph paper, we could put the vertex where we know it's going to end up, and then just pretend that that's the origin, right, the point 0, 0, to find out what the shape's going to be. Okay? You get the idea? Now, something I know happens a lot, when you get into harder math, you have to do this stuff to get it. You can watch this 1,000,000 times, and until you actually do it, you're not going to get it. Your brain it doesn't work that way. In order to actually, the parts of your brain that are active when you watch me do this, they overlap a little bit with the parts that you use when you do it, but they're not exactly the same. So you actually have to do some of the problems to get this. I don't know if you've gotten that far yet, but you got to get there pretty soon, right? So the freebie tests are later this week. We'll come back next Tuesday and we'll review the results of the freebie test, but then next Wednesday is it. That's your in-class day to do this, and then we're moving on to the stuff, right? Okay, so you got to jump on this right away if you haven't. I think this class is in pretty good shape, but just so you know. All right, so what would happen, maybe we won't even do this one, but I want you to tell me with this next one, how is it going to be different? So what are the values of A, H, and K here? A is negative 1/3, okay. How about H and K? H is 1, good. K is -3, good. And so we're going to slide this thing. Where's the vertex going to be? 1, -3, right? So if we're going to graph this thing, if we're going to stretch this thing, well, we know, first of all, the vertex is going to be there. So on the xy plane, we know that the vertex actually has coordinates 1, -3. We're going to pretend like it's at the origin, though, right? And now, how do I do this? Right? If my parent graph is an x² graph, everybody agree? Let's pick a convenient point. So I would go from this point, I would go over 1 and up 1, right? Normally. Over 2 and up how much? 4. Over 1, up 1. Over 2, up 4. Over 3, up 9. Right, so there's my normal parent graph shape. What am I going to multiply my y values by? By A, right? So think about those y values. Which one of those y values is best to multiply by -1/3? Yeah, the 9. Good, right? So if we take that 9 times -1/3 is what? -3. Good. So instead of going over 3 and up 9, we're going to go over 3 and down 3, right? Because of that calculation. So what's this thing going to look like? It's going to look like that, isn't it? Right? It's going to be the one that's reflected because A is negative, and it's going to be squashed. So instead of going over 3 and up 9, we're going to look for the graph in Moodle that goes over 3 and down 3 from the vertex. And where is this actually going to be? Remember, the coordinates are 1, -3. So in reality, this is there's the y-axis, because this is actually at 1, and there is the x-axis, because this point is at -3. Okay, make sense? Okay, all right. Last one for today, I think. How about this guy? Write that function in that form. So what kind of parent graph is this? x². So we just need to know the values of A, H, and K. H and K are simple. What are the values of H and K? Hold on. So there's the vertex, right? What are its coordinates? -2, -3, it looks like. So the coordinates there, -2, -3. So there's H and K. That's easy, right? What about A? So let's use this as a convenient point they've picked for us. So on the dilated graph, we're going to between that point and that point. How far to the right are we going? 3. So from the vertex, if we go over by that color, if we go over by 3, how far? And we're actually going up how far? 3. How far should we go up? Normally on the parent graph. Over 3, we go up 9. Okay, so we would normally expect to go up 3, 6, 9. So clear up there, right? So what's A? A is just equal to the dilated version. What's the dilated y value? So 3 divided by the parent y value, which is 9, so what do we multiply by? 1/3, yeah. Right, makes sense? All we do is plug that stuff in and we're done, no big deal. So our final answer would just look like f of x equals 1/3, that's a, times x minus -2, so x plus 2 squared, minus 3, right? Okay, got the idea? Okay, go, work. Get questions answered?